Good evening. We'll start the session in a couple of minutes, see if anyone else wants to join.
Yeah, sure.
Okay, let's get started. Good evening. I am Shankar. I am the TA for this session today evening on the course Computational Fluid Dynamics, and this is a live session you're attending for the doubt clearing session, and we'll be solving graded and ungraded assignments from this week's questions. So this week we are dealing with uh, turbulent flows, which are basically high Reynolds number flows and is characterized by lack of order. So before I start, let's. Is there any questions from your side?
As we go along, I might have some.
All right, sure. Okay, let's start with the graded assignments for the week 12. And the question or the first initial read up that was given is as follows. Figure 12.1 is again not this one again. I think oh, excuse me, I think I have made the wrong one. No, this is the one, right? Unsteady turbulent developing flow of water with a density of 1000 and a viscosity of 100.001 in the SI units through a rectangular duct of dimensions LWH such that L is very much greater than the length in this direction is very much greater than the length in either of these two directions, and the width is 1.5 times the height. The inlet velocity is uniform across the inlet plane but varies with time as shown. The outlet can be considered as a zero gauge pressure surface. Um, Let me just make sure I have not missed out the equation for uh, the inlet velocity profile.
It's at the bottom.
Yeah. Uh, oh, yeah. This is the inlet velocity profile where V of t is given as V in times 1 plus square root t. So you see that there is an unsteady velocity profile that's developing across the inlet plane, and Yeah, let's get started with the questions that have been asked. The first question is, if h equal to 2 in figure 12.1, the value of velocity, value of inlet velocity for the flow to have a Reynolds number of 50,000 is.
It's 2.1.
Yeah, um, the answer is 2.1. So basically, Reynolds number is given by rho your velocity inlet here in this case times the hydraulic diameter by the viscosity, and the hydraulic diameter is basically 4 times the hydraulic radius, which is 4 times the area of cross section by the perimeter. And in this case, if h equal to 2, then we know that w will be equal to h equal to 2 centimeter. Therefore w will be equal to 2 times 1.5, because w is 1.5 times h is equal to 3 centimeter. Therefore we get the hydraulic diameter to be 4 into 3 times 2 divided by the perimeter, which is 2 times 3 plus 2. And I yeah, so when we solve this, I think we'll get the answer to be 2.083 meter per second. Therefore the correct answer is option B. Moving on to question number 2. We wish to simulate the flow through the duct shown in figure 12.1 using the K epsilon turbulence model. Which of the following statements is or are correct about the Reynolds average Navier-Stokes equation? We need to solve the unsteady form of Rand's equation. We need to solve. We need to. Okay, there is some mismatch here. We need to solve the unsteady form of Rand's equation because the. Let me just get that out. Get the question out.
Because the flow is turbulent.
Yeah. And the third part is we can use the steady state form of the Rand's equation because the equations are time averaged. Which among the answers would be correct here?
1 and 2.
Yeah, we are in fact solving for the unsteady form of Rand's equation, and we are solving for the unsteady form of Rand's equation because the flow is turbulent. Basically, first statement makes sense, and second statement just gives the reason why we are doing it. But even though we have time averaged it, that does not give us the liberty to choose the steady state form of the equation, because we still have a fluctuation in the y and the velocity profile that needs to be taken into account. And when we solve that, we can only solve that using the unsteady form of the Rand's equation.
There is no such thing as a steady state form of RANs, no? And it has to
No, no,
be
Rand's is automatically said to be unsteady.
unsteady. Yeah,
Yes. So that statement itself is wrong here. That's
yeah.
correct. Okay, moving on to question number 3. We wish to simulate the flow through the duct shown in figure 12.1 using the K epsilon turbulence model. How many partial differential equations do we need to solve?
The
What?
continuity, the three
Yeah,
RANs and two K, 1K, 1 epsilon.
yeah. One is the continuity, second is the x momentum, third would be the y momentum, fourth would be the z momentum. Since we are using a K epsilon model, we have to solve each of them now. And K is known as the kinetic energy, turbulent kinetic energy. And the last one, epsilon, is the turbulent kinetic energy dissipation rate. Therefore, we have a total of 6 equations that needs to be solved. And there are 6 equations. So K epsilon model gives a satisfactory solution to a turbulent flow problem. Moving on to question number 4. Which of the following statements is true about the turbulent kinetic energy variation within the duct for the problem shown in figure 12.1? At a given location, not close to any boundaries, turbulent kinetic energy will be increasing with time. Second one, at a given axial location and at a given instance of time greater than 0, turbulent kinetic energy will be closer to the center than close to the wall. Which of
I
the
marked
statement?
both one and two, but apparently only one is correct.
Okay, we see that the velocity profile has an increasing relation with
Correct.
time. So we see that the kinetic energy will be increasing with time because of the velocity. So the first
Correct.
statement is correct. Now,
Why is the second statement not correct?
okay,
I thought the velocity at away from the wall will be higher, no?
uh, so this is the turbulent kinetic energy that we are in fact talking about over here. So when we talk about turbulent kinetic energy, we see that this is given by half u prime m u prime m averaged over the entire one. And I think the answer here is that the deviational velocities at the center is much less as compared to that at the wall, because there is a lot of disturbance or even more turbulence towards the wall than at the center. So therefore, the second point where the turbulent kinetic, this is with related to the epsilon, sorry, k. So therefore, the kinetic energy will be smaller close to the center than close to the wall over here. Is what I think the answer is.
Can you confirm this? Because I always, if you look at all the graphs and all that, you will notice that the velocity
Yeah,
increases
the
from wall
velocity
to wall.
profile will show an increasing profile, but the overall
Correct.
kinetic energy also would be increasing. But since you are concerned with the turbulent kinetic energy, it would tend to be more at the wall because there is more deviation. Deviational velocity will be larger at the walls than at the center. The derivative of the time at the walls would be larger than the derivative of the velocity at the center. Does that make sense?
I don't know. I thought you prime kind of increased at the center.
Let's think about it this way. Suppose we are considering a wall over here. Suppose there is an eddy over here and an eddy over here. The deviational velocities at this point, or the derivative of u prime and the derivative of u prime, which one would be larger? Let's say 1 or 2. Here there would be tend to have a higher differential. If you take the velocity profile, we are seeing that this would be the velocity profile u versus t over here, whereas this one would be a velocity profile over here. Although it was not directly with respect to t, there is a gradient in the velocity as well. Okay, I'll just confirm this answer. I think this is because the fact that towards the wall, the gradient, the wall effects causes a higher turbulence than the center, which leads to a larger deviational velocity, or the fluctuation velocity, which causes an increase in the turbulent kinetic energy rate.
Mm, I'm so
So,
not convinced. Yeah.
all right, fine. I'll just confirm this and just
Yes,
get back
please.
to you on
Yes,
this.
please. Yes,
Sure.
please.
Yeah, moving on to question number 5. Which of the following flows are likely to be turbulent? Flow in a circular pipe at a Reynolds number of 50,000, flow over a sphere at a Reynolds number of 50,000, flow over a flat plate at a Reynolds number of 50,000.
One.
Yeah, only the first one, because the critical Reynolds number in this case, one second, sorry about that.
50K, no? 50 to 100. 50, I
Yeah,
think.
the critical Reynolds number here would be around 2000.
Oh,
The
okay.
yeah, it's 2000. It's to less than 2000 it's laminar, greater than 3000 it's turbulent. It's in that
Okay.
range. So 2000 to 3000 is the critical Reynolds number here. For a flow over a sphere, it's of the order of 200,000 or 2 lakh. And for a flow or a flat plate, it's almost equal to 5 lakh, 500,000. Therefore, only the flow over a circular pipe will be a turbulent flow.
So at a even at moderate speeds, you're going to immediately get turbulence in the pipe.
That's not necessarily true. The velocity is supposedly moderate depending on the fluid that is used. If you have a high viscous and low dense fluid, then velocity can be really really high. It still would be
No,
a moderate
assuming
flow.
let's say same fluid in all three cases.
Um, yeah, as the velocity increases, we would get a turbulent flow at
Yeah,
around the 3000. Yeah, we are using the same.
because it's a little difficult to grasp this concept of turbulence
And also there is not
for
much.
for, for somebody who's just starting. Yeah,
I see. There's not much work that has explored this in a really constructive manner. There are a lot of guessworks that I've done, like K epsilon model, like that,
yeah.
or the mixing length model. But there is a lot of discrepancy in this because of the chaotic nature of turbulence. Okay, question number 6. Mm, which of these are the characteristic features of turbulent flow? First one is always three-dimensional and fluctuating. Second one is high diffusivity, and the third one is they do not obey Navier-Stokes equation. What
First
is
two, first two.
Yeah, yeah, it is always three-dimensional because of the formation of eddies and the formation and the fact that we are describing with the help of a fluctuational velocities. Therefore, they are in fact always fluctuating in the x, y, and the z direction. Therefore, all of these components have a gradient in the axis at which they are flowing. And due to the chaotic nature, they are in fact highly diffusive, and they obey the Reynolds average Navier-Stokes equation. They do in fact obey the momentum balance, as that can't be momentum cannot be created in a energy conserved space. So they do obey the Navier-Stokes equation. Now, one of the characteristic features is here that we can exploit the use of the highly diffusive nature of turbulent flows to create effective mixing and mixing patterns and uh, thermal spacing or thermal uniformity in this manner. So, one of the daily examples that we see is the chai wala, a person who is making tea will tend to mix tea with a large height difference in while pouring in from one cup to the another, and that's basically to increase the velocity and therefore the mixing. And then when we do it like this, we get a thick foam over here, especially if there's coffee and all, has a thick foam that is developed, which increases the taste or whatever it is. Another characteristic thing is that when we have a tea and we are trying to cool it down, we tend to blow on the surface. That's because we are trying to make the flow turbulent over there, and thereby increase the heat transfer coefficient, which is linked through the analogical equations such as Dittus Bolter or whatever in the particular sense. Therefore, we use the we use the highly diffusive nature of turbulent flows to in our daily lives to make use of them. Yeah. So moving on to question number 7, which of the following statements is true about the turbulence closure problem? And yeah, it arises only when we time average the governing equation. It arises when we do direct numerical simulation of turbulence, and it arises because there are too many equations and too few variables.
So that's one, I guess.
Yes, it arises only because we have it arises when we time average the governing equations, because there is a deviational velocity and in the x, y, and z, and because of which we have too less equations and too many variables. So that proves the third statement wrong. And we can directly numerically simulate the turbulence model, such as using techniques such as DNS, which resolves all scales of the motion or eddies by considering a very fine grid. Although that is computationally very expensive, we can do direct simulation of turbulence. But the turbulence closure problem arises when we time average the governing equations, and which leads to more number of variables than the number of equations.
Because we start modeling them using Reynolds stresses, right?
Yes, U bar and V bar, yeah, U bar, V bar, or UI bar,
So we need to solve those. Yeah.
UJ bar, yeah. We model them using these Reynolds stresses, and then we move forward. Yeah, speaking about Reynolds stresses, next
Hmm.
question deals with which of the following statements is true about Reynolds stresses. First one is they are not stress per se, but they are stress like quantities. Second one, there are only six independent components in the Reynolds stress tensor. Third one, they are constant across the cross section of a pipe in a fully developed flow.
One and two.
Yeah, they are not stresses per se, in the fact that they generally don't give out a stress like that, but they are identified as stress like quantities. They are also known as virtual stresses, which arise due to have time averaging. And there are six independent quantities, which are in fact u bar, u bar, u bar, v bar,
Normal. Yeah.
yeah, u bar, w bar, and all the combinations that are arising due to this, which includes v bar, v bar, v bar, w bar, and w bar, w bar. And we see that ui, uj is the same as uj, ui.
You want.
So there are six independent components in the Reynolds stress tensor, and they are not exactly constant across the cross section of a pipe in a fully developed flow. They can be there can be a sudden change, and there can be a gradient of this along the cross section of a pipe as well.
This is where I thought, the fluctuating velocity,
Hmm.
uh, sort of, they're not constant, definitely. So I thought they
Yeah.
would be higher at the center rather than at the wall.
Um.
That's the way I understood it. Yeah.
Oh, with regards to the previous problem, right?
Yeah, yeah, yeah. It's kind of linked to this,
I see.
sort of.
Again, this does not say anything about the fact that it is necessarily higher at the center than at the wall, or the deviational velocity is not necessarily higher at the center than at the wall.
No, but the
Um,
kinetic energy is directly, uh, you know, uh, the product of the two fluctuating
yeah, the turbulent
velocities.
kinetic energy will be the product of the two fluctuating velocities,
And the
and the
same,
fluctuating velocities we can't say certainly that at the center to be more than at the wall. It can be the fact that there is an eddy forming at the edges, then no eddies are formed at the center. So therefore, a higher kinetic energy may be developed at the at the wall rather than at the center. So we're just saying that this statement does not necessarily always be true. Anyway, I'll just
yeah, yeah,
ascertain that after I just discuss with this.
sure.
Yeah. Okay. Which of the following statements is true about eddy viscosity, which is denoted by, I think, ut, and it is a flow property. Second one is it is isotropic. Third one, it is higher near the walls than the near the center in pipe flow.
First two are correct. Third one, I am not sure.
Yeah, it is a property of the flow. So the eddy viscosity is given by Lm square times du bar by dy, and we know that the average velocity will in fact be higher at the center than at the walls because of the no slip condition. We can impose that. So we see that the gradient of that will be higher at the center than at the pipe flow. Therefore, the eddy viscosity will be higher at the center. It is isotropic. That means that There is no variation of the eddy viscosity in the x, y, and z direction. If the eddy viscosity in the x direction is, let's say, 5, then in the y direction as well as in the z direction is in fact 5, which means that it is isotropic.
Yeah.
Okay. Then moving on to the last question for the graded assignments. The units of kinetic energy dissipation rate are, this is epsilon, and which is given by yeah, nu times dou u by dou m times dou u prime by dou m. So dou u prime,
M stands for?
xn, sorry, not m, xn.
Oh, X. Okay.
Yeah, that's the coordinate in that axis.
Okay.
Dou ui here would come, yes. Say dou uj or dou ut or whatever it is. It's just showing that uh, derivatives del of ui uj, del dot ui uj. So that's what is happening here. So we see that uh, the viscosity has a unit of meter square per second. The kinematic viscosity has a unit of meter square per second. Velocity has meter per second times meter, and the dou u prime by dou xm would have a meter per second times meter. Therefore, when we simplify this, we get the answer as meter square per second cube. Therefore, option C is the correct answer. I hope you have got the same answer
I I couldn't figure it out, though I by luck I got, I got it.
here. I see.
Okay, so
Yeah,
that's
I hope
meters.
this one makes sense though.
Yeah.
With
So nu is meter squared by second, per second.
yes, yeah. The kinematic viscosity is the momentum diffusivity, and
Uh,
diffusivity has the unit of meter square per second
meter
in
per.
all. Yeah.
Oh, meters per second velocity. Okay. Okay. So that becomes, yeah. Okay.
Yeah. So before we move to the non-graded assignments for week 12, we'll just take a quick break here and
Sure. Sure.
we'll meet in a couple of
Sure.
minutes. Okay, we can resume. Yes, yeah.
Yeah.
Okay, a couple of four questions for the non-graded assignments for the week 12. Which of the following is a characteristic feature of the turbulent flows? Is it the chaotic fluid motion, high diffusivity, and high frequency
Okay.
fluctuation?
All three. Yeah.
Yeah, these are in fact all three are features of the turbulent flows as we had been discussing earlier. And this is the chaotic fluid motion is the reason why there has been limited research as compared to the laminar flow for the same body or same system. Question number two, the time interval for time averaging of flow governing equations should be such that it should be as large as possible. It should be much larger than the time period of the largest eddy. Should be much larger than the time period of smallest eddy, or it should be much smaller than the time period of smallest eddy.
That should be B.
Yeah, yeah, the ideal scenario would to compute or to simulate or numerically evaluate the value of the flow field would be to have a time step that is just larger than or that is considerably larger than the time period of the largest eddy, because that should not get affected by the time period in which we are dealing with. And if we have a option D where we should be much smaller than the time period of smallest eddy, we would have to deal with a time step of point of a considerably small time step, which would lead to a very high number of uh, iterations, again leading to computationally expensive problems. Therefore, the correct answer is ideally it should be larger than the time period of the largest eddy here.
So in a DNS, it would be D, is it?
Yeah, in a DNS method of solving, we have the time period of solution to be
Or
very,
there is no
very.
DN, or is there no time period with considering? Oh, delta T. Okay. Yeah.
Yeah, we do have a time step that is very, very small in the
Yeah.
DNS
Yeah.
method of
Correct.
solving, and we'll have like in a very, very large number of iterations which need
Correct.
to be solved. Question number three: the mixing length uh, of the mixing length model varies with which among the following? Fluid viscosity, Reynolds number, and the normal distance from the wall.
That'd be three.
Um, the normal distance from the wall is actually correct. We see that the mixing length model refers to some kappa or k times y, and generally this k should be roughly equal to 0.4. Therefore, it does not exactly explicitly deal with the fluid viscosity or the Reynolds number. It they varies with the normal distance from the wall. That is true here in this particular case where we are dealing with uh, turbulent flow. But for a laminar flow, I think there is a different scenario overall, where we have seen the boundary layer thickness to vary as Reynolds to the power 1 by 2 and Reynolds the what do you say the boundary layer thickness to vary as the power of bound Reynolds to the power 1 by 2. Therefore, this statement is very well established. Normal distance from the wall is only for the turbulent flow models.
Okay.
Question number four, we are solving the case of a steady developing turbulent flow between two wide parallel plates using the K epsilon turbulence model. For this case, the number of differential equations that we need to solve is what
I,
would
I
be the
I thought it would be six.
we need to understand that we are solving for two infinitely wide parallel
Parallel.
plates.
Yeah.
So this means that we are considering the x, y, and z. There is no variation in the z direction, or whatever variation in the z direction is actually uh, neglected, or it's not considered in this particular case. But I see that this is in fact a turbulent flow which needs
Yeah.
to consider the z momentum, z
Correct. Correct.
axis as well. I I'm not sure with the answer that the given answer is correct or not. But with the options that is given, I would say the answer is 5 because we have the continuity equation, the x and y momentum equation, and the k and epsilon model equation.
Oh, and also it says steady developing. I mean, how can it be both?
Um, steady developing. Developing refers to the meaning that there is variation in the x direction.
It cannot be
Like
steady, no?
dou u or dou u by dou x is not equal to 0. That's what definite steady. The axial variation of the velocity profile is not equal to 0. For a developed flow, we see that, or dou u bar in this case, dou u bar by dou x. If it is 0, it's called a developing flow, and if it's not 0, it is sorry. If it's a 0, it's a developed flow. If it's not equal to 0, it's a developing flow. So I think the z momentum equation need not be considered since we are solving for the w bar in that equation, and w bar is assumed to be 0. I'm not exactly sure why the z momentum is not considered.
Oh, we said
I
it's 3D at all times. So,
Yeah, we have just established that it
yeah,
is a
yeah,
three-dimensional
yeah.
solution is required for all vector solution.
I mean, just
I'll
because there are two parallel plates, it doesn't mean
hmm.
that.
Yeah, I agree with
Yeah.
that this statement, the argument. I think the answer given, the options given here is wrong. In fact, it has to be 6, 5, 4, 3,
Yeah.
or some other. 6 would have been the ideal
Yeah.
answer
Yeah.
over here.
Yeah.
Yeah, with that, I have completed the questions for this week. If there are any questions, I can spend some time and discussion any of that.
Uh, Last week I couldn't attend the call,
Okay.
so just maybe just one question on that last week's assignment.
Which is
Okay.
question would you like to
One
discuss?
second.
Yeah, I can go through that again if you want to.
No, I mean I got them all except item 8.
Question number 8. So the Boyer-Watson algorithm for Delaunay triangulation, right?
Yes.
So basically, what exactly is the question, or should I just explain? Go ahead and explain this.
No, he says all boundary grids are interested first. No, that's not correct.
Yeah, that is
All
not correct.
nodes are instead randomly correct.
Yes.
This I didn't understand. Item 3. Your number of.
The number of triangles that are produced in the advancing front method now is not necessarily fewer than the one that is done by the Delaunay triangulation. For example, if you see the way that has was described in the class, we see that there is, in fact, let me say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I'm not sure if this number is correct,
Okay.
but yeah, the way at which this was triangulated is exactly the same as the way that was done in the advancing front method in the lecture that a professor had shown. I think the way I have discretized would be incorrect over here. Let me see if I can pull that up. Advancing front method. Uh,
I mean, what is the advantage?
it's just a method to bring about the triangulation. That's just two ways to do this. The Delaunay triangulation does not have a particular arrangement. You can start from anywhere and do
Anywhere.
anyhow,
Yeah.
and the other one would require a set of systematic ordering and start from the one of the border, random border, then move inward towards it, move in the counterclockwise direction, then move inwards. So in the way that was discussed in class, I am taking the uh, work of Professor Srinivas
Hmm.
Jayanti's lectures. So I see that there are one, two, three, four, and there is one triangle here, 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 here. Um, there is one node point here. So this is how it was discretized, and we can or triangulated. We can see that both the advancing front and in the Delaunay triangulation was done in the same way and led to the same number of uh, triangles in each case. Yeah, there were 13 triangles in both the cases. So
Mm.
in the figure that Sir had used to explain, there was actually the same number of triangles. The fewer triangles were not produced in the advancing front method. In fact, a fewer triangles, there would be a case where the Delaunay triangulation can provide a smaller number, and a case where Delaunay triangulation can provide a larger number. In one of the questions that is asked whether we are considering a convex or a concave as
Mm.
shown here, so we see that domain outside is partly included near the concave boundaries, and domain inside is partly included during the convex bound, or inside is partly excluded during the convex boundaries, if I remember correctly, if I had explained this in that sense. So when we triangulate this one,
This would be
like,
what? Concave,
yeah, this is
convex.
this is concave. Convex, no, this is convex, sorry.
Yeah.
Yeah, yeah. So when we triangulate this, there will be a small part over here that we are neglecting. So we are when we do convex, we see that a domain inside the boundary is partly excluded, and when we do concave, what we see is, if we are having a system like this, when we triangulate this as like this, we see that some of the part would actually be
Included.
coming up in this outside of the boundary would coming up. I'm not drawn perfectly well, but yeah, some of the boundary would outside the boundary, part of the outside boundary would be included during the concave the boundaries. Therefore, Boyer-Watson method of triangulation can have a place where that can be more or less depending on how it is, how the body fitted grid is, and
Okay.
therefore this statement is in fact wrong.
Okay. That's it from my side.
Okay, then in that case, I'll just give a brief overview of whatever that was discussed over the last 12 weeks, and then close the session for the day.
Sure.
So, in the first week, we had been talking about the calculation of flow in a rectangular duct, where we have discretized one of the basics of the CFD techniques was used to uh, see how everything was done, starting with a rectangular channel, and we also solved equations for parabol, the cylindrical profile, and yeah, I had explained it with the help of a CFD example problem, how a simple question such as d square u by dx square equal to f of x, where f of x given by here, is done using a CFD technique. Then moving on to week two, it was mainly about how we solve the move up. Yeah, it was about how we have solved the temperature profile equations, or a solution of elliptical equations in that sense, and most of the equations are questions that were related to, in fact, this method of solving. Oh, sorry about that. Yeah, and we have come across some of the introduction to methods of solution over the second week lectures, and I think this would come up in the second week. This I think one of in from second week, from fourth week onwards only I had come up to date. For the second week, it was about triangular geometry and discretization of the triangular geometry using finite volume method to solve such uh, geometries, such as a duct or something. Then moving on to week three, yeah, it was related to the solution of the Navier-Stokes equation and questions related to the Navier-Stokes equation, uh, such as Newtonian flow, fluid assumption, etc., etc. And for week 3 I have done the graded assignments of week 2, which in fact deals with the formulation of triangular geometrical structures. Moving on to week 4, we have done questions based on, oh, sorry about that, we were in, one second, yeah, we were in week 4, and we were trying to solve the mass conservation or this reaction mechanism or reaction CFD with reactions. We are trying to put chemical reactions and CFD together, and trying to use CFD to find out the solutions of flows with reactions or catalytic problems with reactions. And for that we have had particular uses of this particular reaction happening through a entire length of a channel, and we are finding out some solution of that, and we have based questions based on that for week 4. And for week 4, the live lecture contains the problems of the graded assignments of week 3, which included questions based on the Reynolds, the Navier-Stokes equation, the x momentum, y momentum, and z momentum balance, and the continuity equation. And some other problems are associated with the formulation of the Navier-Stokes equation, such as stress and strain relationships. Let me see. For week 5, yeah, for week 5 we had yeah, we were discussing about the consistency and inconsistency of schemes, the convergence schemes. We were finding out the values of A, B, C, D when we have had multiple point methods to explain the derivative of function. And then we have discussed about the derivative of the Taylor series expansion of a function and the expansion such, so resulted as such. Then we also we have for week 4, for week 5 I have done both week 4 and week 5, the graded assignments of week 4 and week 5, and explained it using that. And we see that week 4 always dealt with or generally dealt with reaction associated flows. And for week 6, yeah, this is week 6 in fact, I have not changed the name. We were looking at the schemes, the stability schemes of other methods such as Crank-Nicholson scheme, Dufort-Frenkel scheme for the unsteady diffusion equation, etc. And we have explicitly taken a look at all of this and convergence schemes regarding the Lax theorem and all, and that's what we did during the week 6 lectures. We were looking at the first order of accuracy, inconsistency, and the stability of all the various schemes associated with the CFD techniques. For for week 7, we were looking at the matrix form of the McCormack scheme, the other uh, beam warming method, etc., to find out the solution of compressible flows. And we saw how to numerically solve such equations the based on how we do the problem. We see that it is easier to solve a compressible flow than an incompressible flow, because the density variation can be taken into account and can be solved based on that. And the compressibility is based on something known as the Mach number, as I have explained it in one of the lectures there. And the Mach number is basically the speed of the fluid to the speed of sound in that medium, and that alone dictates whether it is compressible flow or not.
Yeah.
Okay. Moving on to question week number 8, we have incompressible flow method solution, which deal with coupled in pressure and velocity and nonlinear in velocity as well. Therefore, we were looking at how to solve these methods, and we excuse me, we were looking at pressure equation, pressure correction method, and a couple of more methods that were given in that. Simple is a perfect example of that. Simplex, simpler, smack are all used to solve pressure linked, pressure coupled velocity equations to get the profile of flow in a incompressible flow method flow. And most of these equations used finite volume method to discretize and solve. Yeah, Mayan just dealt with the solution method of the discretized equation. I think, yeah, all of this would have solved. We have only discussed about how the Gauss elimination, the LU decomposition, the Gauss Seidel and TDMA, and all the other techniques to find out the uh, solution of the discretized equation. And we see that the iterative method can be computationally uh, less involved than non-iterative methods such as Gauss elimination or the LU decomposition. And the iterative method therefore is preferred over that for that particular reason, the ease of computation. But we see that iterative methods have one necessary condition that is written here. It should be diagonally dominant. If it's not diagonally dominant, if all the rows are not, if all the rows have to be diagonally dominant, and at least one row should be strictly diagonally dominant, only then we will get an iteration scheme to be converged. Otherwise, it will keep on diverging. And in that particular week, we have solved an equation question where one of the answers was in fact highly diverging. If I can pull that up.
Yes, yes, I was there on that call. Yeah,
Yeah, yeah, yeah. We see that the residual, which is actually discussed
kept
in the next
increasing.
lecture.
Yeah.
Yeah, which is actually discussed in the next lecture, seems to be increasing with the number of iterations. Moving on to week number 10, we were continuing the discussion on the iterative methods, and we were trying to see the other methods that can be used, such as the successive over relaxation, the multi-grid method, which uses a small grid size, and then we move it on to a coarse grid to eliminate the small wavelength and the large wavelength respectively. The SIP method and all other methods which uh, are used for the ADI method, etc., are the iterative methods which were discussed in the week 10 lectures. And I think there was a couple of questions that also we had done on the analytical solution of the solution for finding out the flow profile through a rectangular channel that was discussed in the week 1 and 2. And we had tried to explain how we can analytically describe the solution through a series of mathematical manipulations, and ultimately, we arrived at the final answer over here with the help of a Fourier series expansion. We would be getting this, and the understanding of this is very complicated for such a simple system. Therefore, no one usually does it in an analytical solution to find out the answer over here. And in the previous week, as I had just shown earlier, we were discussing how the triangulation of the unstructured grid and the triangulation of the unstructured grid using Dillon the Boyer-Watson method and the advancing front method, and we see how what the uses of a unstructured grid is over a unstructured grid could be, and how to bring about the unstructured grid into the domain that is being considered is what we had done in week 11. And finally, for this week, we had just gone through the basics of turbulence, very fine, simple basics of turbulence, and how to solve the Reynolds average, the Navier-Stokes or the Rance equation using mixing length model and the K epsilon model, and the features of turbulent flows. So I think that's all I have for today's live session. If there are any questions, I'll be happy to answer them. Otherwise, that's the end of this session.
I'm done. Yeah.
Yeah. Okay then.
Right. Good
I'll
night.
be hanging around if anyone else wants to join and discuss any other further questions. But if there are no more questions, we can leave here.
Yeah, sure. Good night.
Yeah. Good night. Thank you. By the way,